Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 35 on electric circuits. So, you're all familiar with probably a flashlight. Yeah, I see I've turned it on, which is a simple flashlight, and I can turn it off and on by pushing on the switch. I used to have a little yellow flashlight when I was a kid, and you just slid the little slider back and forth, and that turned it on or off. And what's going on here is we've got our battery. And it's probably a AA or something like that. So I'm going to say 1.5 volts. AA batteries are 1.5 volts. And it's attached to a metal.
A AA does not look like that, Mom.
I'm just drawing it this way for the picture. And it's got a bulb, an LED bulb. In the old days, when I was a little girl, I used to play a lot with these flashlights that had incandescent bulbs in them. And if it was an incandescent bulb, we had a little filament. This was like a light bulb, and there was a little filament. When you put current through that little wire, it would get really, really hot and make light. And so what's going on here is the current. So this terminal here is going to be positive and negative end, so there's a difference.
No, Mom, the positive and negative ends are on the different ends of the battery.
I know. For this, I'm just drawing it like a 9-volt battery. Okay, so the peanut gallery, well, it's going to draw it like. All right, now are you happy?
Yeah, now I'm happy.
Okay. So we've got a positive and negative end. So here we have a voltage, say, of 1.5 positive, and here's 0 volts. And the current flows through that filament. And then I have a switch. Remember? My switch on, switch off. What the switch usually is when you switch it off, it opens. When you switch it on, it closes. And then the current can go through and it lights up. When you want to turn it off, you hit your switch and it opens up again. So that is a very simple circuit. And now we're going to do it in sort of the notation that they like to use. So this same circuit, and they like to draw batteries looking like this. And we will draw light bulb, give some resistance. So this is how we would draw this circuit with our battery and our flashlight. Oh, and then the switch. How do they draw the switch? I'm trying to remember the official. I always just draw the official way to draw the switch. Right, they like doing it something like this, like a little thingy mobber. Okay, Isaiah, turn that off. Okay, so here we can see the battery. This is the symbol for the battery. The different voltages with the lines. This is our little switch, and this is the resistance of this guy here, of the bulb. Light bulbs have resistance. Okay. So now we're going to make it more interesting. We're going to say, well, what if I want to draw, instead of a simple flashlight, what if I want to draw a Christmas light? Instead of Christmas lights. So here we've got our voltage change. Jenny, can you go to the office and get me a new marker? This one's not very good.
Oh, where are they?
Black one. It's in the box.
I'll do it.
Thank you, Kazia.
In what box?
It's in a box. Okay, so here we're going to draw. So in this case, we've got our first little light bulb, and it goes through. And our second little light bulb, and it goes through. Third little light bulb, let's just give this 5 light bulbs, okay? And it comes back. Okay? And if we plug it in, they all light up. Well, if we were drawing this in the official way, we would draw these as just looking like little resistances. So this is our first light bulb, second light bulb, third light bulb, fourth light bulb, fifth light bulb. Thank you. Okay. Thank you. Okay, so now we've got this is our Christmas lights. And so you plug it in and all the lights light up. And if you're familiar with Christmas lights, sometimes you plug it in and they don't light up. So what happened? Sometimes one of these light bulbs burn out. If you look really closely at the tiny little bulb, you'll see the little filament here broke. And what happens? Now no current can flow through. It breaks. It just breaks the whole line.
What's
So
good
then
on
you're going
just
around
one
poking
will
it.
light up?
What?
What about when just one will light
I
up?
have cut the thing is now Christmas lights, they're trying to wire them differently because people got so frustrated with, they used to say, find the bad bulb and replace it and then the lights will work again. And you're trying to find where the break in the line is, but it wouldn't be so simple. There's like the whole thing knocked out. Like I used to think, the ones will light up before then. But it's not that simple. I can't remember why. But basically, people got frustrated with this model of trying to find the bad bulb in the Christmas set. Oh, right. Now I remember why. It's not going to light up. It can't light up when one of them breaks. Look, just common sense. Because there's no current. It stops. So there is no current through this bulb. He's not going to light up. Because look, there's nowhere for the current to go. It just ends. And so it doesn't even move. It doesn't even bother. There is no voltage. Like this is now, this section, because it broke, this, say this is plugged into the wall, so let's say it's a voltage of 110 volts. This entire section is 110 volts. But it's not moving. It's like having a dam. It's not moving anywhere. So it doesn't light up because there's no current.
Why'd you say
Sorry, sometimes I call things heat. So that's why it was so frustrating. Now I remember why it was so frustrating when one bulb breaks is that it's not like these will light up because the current stopped. There is no current, and so it's not going to light up. Even the whole thing is sitting at that voltage, but there's no voltage drop. You need a voltage drop to get the current to go. In the same way you need a gravity drop to make the water flow down. And so it's just hanging out. It's just sitting there, and they're all dark, and it could be this one broke. It could be this one broke. It could be this one broke. You don't know. So I remember once blindly sitting there just trying to pull out every bulb and replace it with a good bulb and try to figure out where it was. So people got really frustrated with this, and they started wiring.
Work?
I think I finally gave up through it. I remember your grandpa, he was able to find it. But because of that, people got sick of wasting time on Christmas lights every year trying to find out where the bad bulb was, and they now wire the newer Christmas lights. They usually wire them differently. But this is called a series circuit. As you can see, any break at anywhere will just stop all the current because the same current goes through all the resistors. So let's look at that. Let's look at this. This is called in series. This is called when things are wired in series, because look there, it's just like a little series. They're in a row in series. So let's see something. Well, we can see that the same current, just common sense, and they all have the same current being pumped through them, right? So they all have this. So in series, we have the same current through all resistors. Same current, I is for current, through all
Why is I for current?
It is.
Because there's no I's in current.
All right, now, maybe it's a different language. All right, now, we can see that the voltage will drop over each of these guys, because remember, V equals IR. So we've got the same current. So let's say this is a 1 ohm resistor. This is a 2 ohm resistor, a 1 ohm resistor, a 3 ohm resistor, and a 4 ohm resistor, okay? We know the voltage on this side here is 110 volts, right? We say, well, it's going to drop. We can find out the total current that's going through the system. So we've got 110 volts, and we say, well, the current isn't really, so we say how V equals IR. Well, what's the R? Well, we just add them all up. Why? The current doesn't really care if it has to go through. It's going through all of them at the same time. So if you just like glued all those resistors together and make what we call an equivalent circuit, it doesn't really know the difference. So I just took all those resistors and I just glued them all together, and I got this. And now I've got an equivalent resistor of 1 plus 2 is 3 plus 1 is 4 plus 3 is 7 plus 4. Now I've got an 11 ohm. This feels exactly the same to the current.
Why are some
go
1
and some
once, 2 and some 1 and
split
some
up.
3 and some 4?
It's still going through it. What? I'm just saying these are the different resistors. So they've got different resistors. Each of these has a slightly different resistor. So now I just turn it into the equivalent resistor. So in series, when I want to find the equivalent resistor, I just add them up because it doesn't really, the same current is having to pump through each of them. It doesn't matter if it gets little breaks in between or if it's jammed together. It doesn't matter. It's the same current going through it. So I can use this to say, well, what's the current? I use Ohm's law. Well, the current is going to be the same. The total resistor, so that I equals V over R, right? For this guy, I just rearrange the letters. I equals V over R. Just divided both sides by R. And now I say, okay, so I've got 110 volts over 11 ohms of resistance. And the answer is 110 divided by 11. I've got 10 amps. So that tells me there are 10 amps of current going through this guy. So now I can go back to this guy. Remember, it's the same, because remember, the equivalent resistance is the same. Sweetie, shh, shh, shh.
How do you make it turn on?
this switch right here. But we're going to get to that later. Okay, so now we're going to say, okay, so what's the voltage drop between each of these points? Because remember, Ohm's law is true for each of these guys. So we said, well, we know there's 10 amps of current being forced through it. And so what is the voltage drop? Well, here we know it's 110 volts, right? Because it's connected to the set of the battery. We'll get there. So here we've got 110 volts. Well, what happens here? I'm going to use a different color. Because yeah, is this too small, or does this show up on the, can you see this or not? Is this too thin? Does it show up on the video? This is 110 volts, and now it's going to drop using Ohm's law. We know
what, Mommy? Is what too small?
Mom, I think it might be too
Too
thin.
small. Okay,
I can barely see it.
You barely see it? Okay.
Barely kind of see it.
Okay, so now we've got 110 volts here, and then we know that it will drop by well, how much? By the current 10 amps times the resistance 1. So it's going to drop by 10. It's going to drop by 10. Plug in the resistance for 1 ohm times 10 milliamps. We're going to get a 10 volt drop. So now it's only 100 volts on this side. We can think about this as a waterfall. Okay. Each of these drops, it's dropping. The voltage starts up here at 110 volts. And by the time you get to the bottom of the circuit, it's down at 0 volts. But each of these resistors is like a drop in the voltage. You can think of it as a waterfall, and there's like drops down it. So we've got, now it's dropped to 100 volts. All right, now it's 2 ohms. So we plug in we say, well, how much is the voltage drop here? And so we plug in, sorry, I had V equals, right, I was calculating the voltage drop. So we've got resistance of 2 ohms, and the current is the same. Remember, the current, same current as the squirt through all of these guys. It's 10 amps. So now we've got 10 amps times a resistor of 2. It's a 20 voltage drop. Now we're down to 80. Okay, 80 volts. All right, next, what's the voltage drop over this? Well, we've got the same current. Remember, we've got 10 amps drops over one resistor. So we plug that in. Resistor 1, 10 amps. It's another 10 volt drop. So now we got on this side. It's now 70 volts. Excuse me. Okay, sorry. I was trying to write V there. It might be hard to tell. I'll just erase the volts. These are in volts. So we got 70 volts. All right, now what's the drop over this? Well, remember, current is still 10 amps times 3 ohms. It's going to be 30 amp drop. Now we're down to 40 volts. Well, what's the voltage over this? Well, we could just cheat and say, haha, it's going to be 0. We know this because of the battery, but I'll show you the hard way. So we'll say, okay, the current is 10 amps times the resistance of 4 ohms. That's 40. So it drops 40 volts, and now we're down to 0 volts, and this shows you our circuit. That's how you solve a, Miriam, can you go sit down, sweetie? Now that's how you solve a
Miriam, go sit down.
voltage drop. This is how you solve a series circuit. Excuse me. Now you can see that as the voltage drops, the brightness in the lamp correlates to the voltage. And so as you can see, as we add more and more bulbs to this, the voltage drop over each one, it'll be dropping the voltage more and more, and so we're going to end up with dimmer and dimmer lights. So as we add more and more lights to the circuit, the voltage will drop more and more. You'll have lower and lower voltages to deal with over they're all sharing that voltage, that one voltage dropping down. So if you think of this, it's like that height of the voltage drop is how bright those lights are. When we add in more, they are not as bright. Okay. Now we're going to deal with the parallel circuit.
That's what happened.
So parallel circuit.
If we have the chance, we are going to do this.
Okay.
I don't think we'll get it.
So in a parallel circuit, what's going on here is we have point A and point B, okay? And then we branch off. So we have our first branch, our second branch, our third branch.
Fourth branch, fifth branch.
All of these have, say there's 110 volts here. So B equals 0 volts, right? Connected to this end of the battery. A equals 110 volts because it's connected to this end. The voltage drop happens over these guys. However, the current is now no longer the same through all these branches. Well, the current will be, you can have equivalent current, but it's not the same current. That connection electron that's coming through here either picks path A, well, I shouldn't say I used A and B, okay. So it either picks little resistor D, resistor E, or resistor F to go through. When you've got that little connection electron coming here, he has to choose which path to go through, okay? So let's say D here, let's say D here is, let's say 5 ohms. And let's say here, resistor E, let's say is 3 ohms. I should have said that 2 ohms. And let's make resistor F into, let's do 10 ohms. Okay? You can imagine a lot more, the electrons, the current is going to choose the path of least resistance. So which of these 3 paths do you think is going to have the highest current through it? E, clearly. A lot of them are going to go through E, and then as this gets jammed up with more current flowing through it, some is going to go through here and here, but the most is going to go through the
second most through D.
Second most through D, and the least amount of current is going to be flowing through F. So, if you remember with our series circuit, the same current goes through all of the resistors, but there's a different voltage over each resistor because of a drop. It's the opposite. In parallel, oh, this marker's no good. Okay, I'm just going to mark it. In a parallel circuit, you have the same voltage across all of the resistors. Remember, because this side is connected to this battery terminal, this to this battery terminal. So it has to have the same voltage drop for all of them. But there will be different current through them, proportional or inversely proportional to the resistance, because the currents want to go through the path of least resistance. Now, so we say, how do we find, remember how we did the equivalent? How do we find the equivalent circuit for this guy? And in this case, well, let's make it simple on ourselves, and let's make them all have the same. Let's make it easy on ourselves. Okay, so let's say they all have a resistance of 10 ohms, okay? Well, in this case, they actually do have the same amount of current through flowing them, different connection electrons. It's not the same, it's not the same current, the same water, so to speak, squirted through them all. It's different water, but they all get the same amount, because if they all have a resistance of 10 ohms, they're all going to get 1/3 of the overall current, right? Because they're all equal. So they're all get 1/3 of the overall current. So in this case, quick note, Ohm's law applies to each branch individually here. So Ohm's law always applies, but here we can use Ohm's law to find how much current is totally going through this. So the hard way to solve it, not using the equivalent stuff, the hard way to solve it is we say, okay, we know the voltage drop, we know 10 ohms, we know the resistance, so we can tell you the amount of current that's going through here, right? So we use Ohm's law, we want to know the amount of current, so we've got V equals IR, I rearrange the pieces, and I get V over R equals I. So I say, okay, I know the voltage is 110, and I know the resistance is 10 ohms, so I've got 11 amps going through branch D. 11 amps, okay? And I say, okay, now I'll do the same thing, the math exactly the same. I've got 11 amps going through branch E, and I've got 11 amps going through branch F. Okay, so that means the total current flowing here and here is going to be 33 amps. You see that? Because each of these guys is following Ohm's law and drawing 11 amps of current. And so we've actually got 33 amps are flowing through point A, splitting up here 11 amps each, rejoining again, and 33 amps are flowing this way. So that those 33 amps get split and rejoin and come back. That's a lot of current. Okay, so then we say, how do we find the equivalent resistance through these guys? And I'm going to have to erase something. So I think it's time for our series circuit to go. Okay. What ends ends up happening here is actually kind of cool. The more branches you add, the lower the overall resistance of the circuit. You might say, what? But think of it this way. I know that if I add another branch here, it'll draw yet another 11 amps. And now my total current is going to be 44 amps. And I know that if I draw yet another branch here, you know, with the 10 ohm resistor, I'm going to get another 11 amps. And now it's going to go 55 amps. Right? So because I know in Ohm's law, just looking at this, I know that the bigger the current, or I should rather say, I rearrange it like this, by Ohm's law, I know that the more resistance I add, I know that the more current is going through, hold on, I got myself all turned around here. I know that the more current that I'm pumping through this system, the more the resistance, see, V equals IR, for the same fixed voltage, so yeah, this is the formulation you want, V equals IR. And you can see that if for the same, voltage doesn't change, the I keeps going up, that way the R must be going down. This is me trying to reconcile in my brain the math would look at this. I'm saying, if for a fixed voltage, I could just keep getting more and more current, that means the resistance must be dropping. And this is actually true. The more resistors I add to a parallel, not to a series circuit, that actually does the opposite. But the more resistors I add to a parallel circuit, the more branches I add, the greater the overall resistance goes down. Remember, in a series one, the more resistors I add, the greater the overall resistance goes up. It just adds. But here, the resistance actually is going down. Now you might say, how does that make sense? Well, it's a lot like a bunch of people trying to get through a crowded stadium. The more doors you open on that stadium, the faster the people can move. The faster that current, those people moving out of the stadium goes, because there are more paths. So as weird as it sounds, adding more branches and more resistors, you're actually lowering the overall resistance of the circuit. Okay. So there's a nice illustration of this. Let me see, in the book on, chapter. There's a nice illustration of this. You could see on page 555. You can imagine, or I'll just draw it here. You can imagine if you've got an 8 ohm resistor and another 8 ohm resistor. Your little guy, your little conduction electron is doing twice as much work. He's got to get through both of those, right? So the equivalent one for this is series, is a 16 ohm resistor. But now, your little guy is going through a parallel circuit of 8 ohm resistors. Now you put them in parallel. And now your guy can actually, they've got twice as much wire to get through. Or they could split up and go through this one or this one. And the weird thing of all is this turns into the same as if you just send it through a 4 ohm circuit. It's weird, but it works. And this is what all modern electricity and stuff is based on. It's weird, but it's true that it actually halves the amount of resistance. So the equivalent resistance. So the equivalent resistance of this guy, of me having 1, 2, 3, 4, 5 10 ohm resistors, is actually, you add it. Let's do it in pairs. Okay, so we want to do off because it makes it easier on ourselves. So let's do it pairs. So let's say 4. We've got 4 D, E, F, and G. Okay, we've got 4 10 ohm resistors. And we say, okay, so I'm going to just add up them in pairs, remember? So I can say, okay, so just look at these two guys in parallel. That means these two guys are the same as a 5 ohm resistor, okay? And then I look at these two guys in a pair, 2 10 ohm resistors. That's the same as a 5 ohm resistor. And now I've still got these two guys in parallel. And so now I'm saying, okay, that's the same as a 2.5 ohm resistor. And you say, whoa, how can that be true? How can 4 10 ohm resistors just be the same as a 2.5 ohm resistor? Well, remember when we did 4 10 ohm resistors, remember how we calculated 44 amps? Because we did the voltage drop over each one, it's 11 amps, that had to be 44 amps. Sorry, 55 is when I had 5, but I just put it under 4. So if we know that there's 44 amps, we say, well, does this check out? Does the math check out? So we try it out, we say, okay, 110 volts and times 44 amps times V equals IR, 2.5 ohms. So the 44, that was current, so it will be in amps, this is in volts. And sure enough, 44 times 2.5 is 110. It works. So it's pretty cool that it seems non-intuitive when you're like, wait, why would it be less? But just think about that crowded stadium with those guys moving outwards and you've got more doors flung open. And so the irony is with a series circuit, the more resistors you add, very intuitively, you're just adding more resistance to the circuit. But to a parallel circuit, the more resistors you add in parallel, so really it's the more branches you're adding, the less resistance there is in the circuit, the more current it's drawing. Remember how I just added those resistors and more current was being drawn? That's why you don't plug too many things into your outlet. Because in your house, a single circuit, when those plugs on a single circuit are wired in parallel. That's why your toaster oven breaking doesn't make all your lamps go out. And that's why you unplugging your toaster oven doesn't make all your, well, I mean, they've also got like those little prongs and stuff. But anyways, so basically, this is why they don't want you to overload a circuit. Wait, sweetheart. Yeah. Because you can just keep pulling more and more current. If I just plug in more and more toaster ovens to a single circuit, I can pull in so much current that so much current is trying to tear through that little 12 gauge copper wire that at some point the metal overheats, melts the insulation, starts a house fire. That's why you have a circuit breaker. Because a circuit breaker is trained that if I try to pull more than, it depends on what it's set for. So you can set one for 10 amps. I've got circuit breakers in my box that are set for 15 amps. I think the oven is set for 40 amps, the oven circuit. But anyway, so as that little circuit breaker is taught to pop when there's just too much current being pulled. And that's what stops you from starting a house fire by plugging in too many toasters. Okay, question. What was your question?
So my question is, so the difference between why it makes one of them it makes it easier and the other one it doesn't, is if you have a room in one of them is if you make the exit hallway really yes. long versus you have many different exit hallways.
Yes, exactly. So with a series circuit, you're not going to make things better, help your guys leave your stadium by making a super long hallway. That's more space everyone has to squash in as they're leaving the stadium. But by adding many more exits, that's what you're doing with the series circuit, you are actually lowering the resistance. That's why with parallel circuits, you are increasing the overall resistance and decreasing the overall current by adding them in series. But in parallel, you're actually decreasing the overall resistance and increasing the overall current being drawn. Okay, so now we're going to have fun with some schematics a little bit because this is on your homework and it would be nice for you guys to see more practice problems. Makes it easier. And it's actually quite fun drawing these little schematics. Okay. I mean, Mama's going to need 2 hands, okay? Put you down. Want to go watch Super Bowl? You want a bottle? Okay. Sarah Grace, do you see the bottle over there on the hallway? She put it down there, right by the Duplos. Can you put some? Okay, so we're going to do some schematics here. So we're going to do some sample. No. This is for magnetism. This is the next lesson. So I'm going to do some schematics here. Okay, so this is from page 556 on your book. And he draws this really wild-looking circuit.
Oh, it's almost worse.
Woohee, stop jumping in the camera.
All right, so we got this wild-looking circuit here.
Hey, Mommy, did you tell them it was Ruby's birthday?
Yes, it's Ruby's birthday. Okay.
The person who just jumped in the camera.
So let's draw. All right, so we've got some wild-looking schematics here, and I think this is 2 ohms, 2 ohms, 2 ohms, 3 ohms. Okay. So we say, okay, so how do we find out the equivalent resistance? If you boil this all down to what does the battery feel, how do you, oh, don't shake it, sweetie. If the camera goes over, it's, okay, that's what you did
last time.
All right, now, we've got here, so we say, okay, so we remember the rule. We've got 2 branches, so we know that the 2 ohm, this guy turns into half. So it just turns into 1 ohm, okay? And then we say, wait, we know how to add in, these are in series. So they just add up. Remember, it doesn't care if you move these guys together. So we're going to do that. We're going to move them together. And then this is going to become a 3 ohm. And now we say, oh, wait. Now we've got 3 ohm and 3 ohm. But they're not in parallel. So let's just not, oh, add at 1.5. No, look what they're doing. Look how the current is moving. These are actually in, oh, they are in parallel. Never mind. Okay, in the book, I'm doing it with the battery there. I didn't realize he actually had the battery on the other side. Okay. Well, me solving this problem where this is a series circuit, then they add up, you know, it's like we scoot them together, and we just end up with a single 6 ohm. Now, if you're doing it the book's way, which I didn't pay attention to the schematic, if you're doing it the way in the book, he actually has a different setup where he's got, this is his point A of his battery, and this is his point B. And these, he didn't actually draw the battery, but it's coming way down here to the battery, okay? And then he draws this whole schematic. So he's got this 3 ohms, and then he's got his 2 ohms, and he's got his another, this is 2 ohms, this is 2 ohms. So the way he does it, you know, again, these two collapse down, 2 ohm, 2 ohm, this becomes a 1 ohm.
Sarah, get out of the camera.
And then these two are in series, so these become a 3 ohm, 3 ohm. And then we've got these in parallel. So these collapse down and become a 1.5 ohm. And then this is what all the battery feels. All the battery feels is 1.5 ohm resistance. So that's kind of cool. And then he's got an even more crazy looking one. It's okay, baby girl. It's okay. Hey, Jenny, can you go put on maybe strawberry shortcake? Superbook or strawberry shortcake? Go put it on. Yeah, you can want strawberry shortcake just for now.
Strawberry shortcake? Okay.
Okay, so now we've got another situation where we've got a 60 volt battery. And we've got, so we've got 10 ohms, 10 ohms.
Mom, Superbook's already on.
Oh, okay.
Mom, but can you get
And then we got 2 branches here. Okay. So now we've got, let's see, we have 16 ohms here, 8 ohms, 8 ohms. Okay, so we say, what does the battery feel? What's the equivalent resistance? Remember, a lot of times we need to solve. Yeah, you could adjust to. You want to find the equivalent resistance to find the current in the thing. Remember, E equals IR, Ohm's law. So we want to find the equivalent resistance because instead of sitting there and calculating Ohm's law for every little piece, we want to do the equivalent resistance and just calculate it. So here we say, okay, we've got. Oh, and then. And then you can't, by the way, you can't just calculate Ohm's law for every little piece if you don't know what the voltages are. Remember, if you've got in series, the voltage is dropping, and so then it makes it more complicated. So you want to solve for the equivalent resistance, find the currents, and then you can go back. And, anyway, it depends on the problem. But, all right, so what we're going to do is we're going to break this test. We've got 8 ohm, 8 ohm, so that is the same. Remember, using parallel circuit rule. That's the same as half, 4 ohm. Now these are in series, so this adds up. Remember, we move them together. It's 20 ohm. 20 ohm. Now these again are, we can just scoot them together. These are in series with each other. So this just becomes a 20 ohm. Now we've got these in parallel, right? Because this potential, we could say is A, this potential is B, right? 60 volts, 0 volts. So now we've got 2 20 ohm guys, and that becomes the equivalent resistance of just 10 ohms. And then it's very easy to calculate the current because we've got the voltage, so we just do 60 volts divided by a 10 ohm resistance. We know there's 6 amps in this circuit. Now that you have that, you can go back and calculate, various other things with the voltage drops and whatnot. But it's kind of fun. It's like a puzzle. It's like one of those logic games people play on their phones all the time for fun. Okay, you could cut the lecture. Jimmy,
Oh, okay.
Can you stop it?
Pause it.
No, stop it. Stop.